Okay, so welcome everyone. Great pleasure to introduce today's second Marvel Classics in molecular and materials modeling. We'll have today Antoine Georges from the Flatiron Institute and the Collège de France, and Gabi Kotliar from Rutgers University and Brookhaven National Laboratory to have an afternoon, or at least on this side of the world, dedicated to dynamical meanfield theory. This is a series that is organized together with SECAM, based here in Lausanne, headquartered, and there is Sara Bonella today, Deputy Director of SECAM, together with Marvel, that is the Swiss National Center for Computational Design and Discovery of Novel Materials that I direct. Before going into today's event, let me also mention a couple of activities that are going to take place in the next few days. On Tuesday, December 13, there will be one of the Marvel Distinguished Lectures will be given by Heather Kulik from MIT in the United States. And on Thursday, December 15, there will be instead a second event, what is called the Mixed Generation Series, with both a senior speaker and two junior speakers, and the senior speaker will be Stefano Baroni from SISSA in Trieste. And they all start at the same time as of today, that is at 3 p.m. Central European Time. You can find more information on the NCCR Marvel or on the SECAM website. But having said this, I mean, let me welcome here both Professor Antoine Georges and Professor Gabi Kotliar. Thanks a lot for accepting this invitation. This is always a very exciting event for all of us because it both goes, with some depth into the fundamentals of novel methods and formalism that have been introduced in the community. We try to alternate, say, electronic structure methods and maybe more statistical mechanics methods. But also, as you see from the agenda, it leaves also some space at the end to go in a more relaxed fireside chat mode, in which we really just have an open interview and some recollection with the speakers of the day. So we'll start in a moment. I'll introduce the first speaker. Let me remind everyone that we'll use the question and answer pane for question and answers. So that the agenda is roughly, we allocate 50 minutes for each talk with a break of 10 minutes. But in this 50 minutes, and it's a little bit flexible, but there will be question and answers at the end of the first talk, and also at the end of the second talk, and also during the interview. I'll read them from the question and answers pane, or if some of you is available, we'll also go live just to make it a bit more exciting. So you are welcome to write your questions at any time during the talk, but we'll have them at the end of each individual talk. And so I see both Antoine and Gabi. Very warm welcome. I think probably early morning, sort of from the east side of the United States. Thanks again. So I think I'll just briefly introduce Professor Georges first, and then we'll go into his talk, and then we'll have a 10 minutes pause, and then I'll introduce Professor Kotliar later on. Okay, so I mean, again, no need of introduction really, but Antoine, I'll use the first name, is both a professor at Collège de France and also the director of the CCQ Center at the Flatiron Institute in New York. After an early start in statistical mechanics in disordered system, has really dedicated, the core of his career to the physics of interacting quantum systems, and in particular materials with strong electronic correlation that will be really The topic of today's talk is one of the inventors of dynamical mean field theory, and actually dynamical mean field theory was the reason why he shared the 2006 Europhysics Condensed Matter Prize, the 2020 Anizur Rahman Prize from the American Physical Society, and the 2022 Feinberg Medal. I should also mention that besides his affiliation and appointment at Collège de France and the Center for Computational Quantum Physics, he does have an affiliation at the University of Geneva, so we have sort of had it also in the Swiss environment and also in Marvel as a member, and is a member of the French Academy of Science. With this, Antoine, I leave the floor to you. 40 minutes for a talk. I'll give you a reminder after 30 minutes, but it's all flexible. Thanks again, and the floor is yours.
Thank you very, very much, Nicolas, for this warm introduction. Let me see if I can succeed in sharing my screen. Does that work?
That's great.
Okay, wonderful. So hello, everybody. So this will be the first of two lectures by myself and Gabi about dynamical mean field theory. And what we would like to do is to give you a glimpse into the sort of conceptual core of the theory, how it is used in practice, and especially what are the prospects for the future. So what is really dynamical mean field theory? Well, it's really two things. It is both a theoretical and computational method to approach the many-body quantum problem. This is a method which is controlled in some limits and which can be used to actually address the physics of concrete materials, taking into account their structure and chemical composition. But it's also a conceptual framework to think about materials with strong electron correlations in a way which is different from the standard solid-state theory textbook, I would say. And I hope that for these two talks, you will see what I mean by that. But before I go into any of this, I would like to say that dynamical mean field theory, as science in general, is really a collective enterprise. And over these 3 decades, I've been fortunate, and we've been fortunate, to collaborate and interact with a very large number of people who contributed to my understanding of condensed matter physics, and especially to the elaboration and applications of DMFT. And it's impossible for me to quote everybody, but I've put some names on that slide. I'm sure I forgot some, but I really would like to express a heartfelt thank you to all the people who contributed to the field. Okay, so before I go into DMFT itself, I would like to say a few words of motivations. Materials with strong correlations are characterized by the emergence of collective phenomena, and often also coming with a number of competing phases. And here on the right, you see a beautiful time-honored example, which is the phase diagram of V2O3, vanadium sesquioxide, as a function of temperature and either substitutions or pressure. And you see that in this phase diagram, already there are 3 interesting phases. There is here at low pressure, an intermediate temperature, a paramagnetic multi-insulator, which you can view really as a collection of local moments with the hopping of electrons being blocked by the strong Coulomb repulsion. So we have localized particles basically with fluctuating spins. If we apply pressure, this paramagnetic multi-insulator can become a paramagnetic metal through a transition, which here is a first order transition line. And the paramagnetic metal, we can discuss whether it's a good or a bad metal, but if you think about the snapshot of the wave function at any given time, it would be something that has many more double occupancy and holes than this phase. And then eventually at low temperature, obviously these local moments have to do something and they order around ferromagnetic. So you see that by tuning some parameters, we can switch the system between different collective behavior. And an important thing to say about these different phases is that for several of them, describing them in terms of independent electron theories actually fail. Interestingly, these very simple phases here, where the local moments are fluctuating and the electrons are localized due to the strong Coulomb repulsion, is particularly difficult to describe within, say, conventional band structure theory. There is no symmetry breaking, which, say, in LDA plus U, for example, would open a gap, but the system is localized just because of charge blocking. This complexity of phases is by no means exhaustive. For example, here, this is an organic material that has a sort of similar phase diagram, insulator, metal, antiferromagnetic insulator, but on top of that, it has superconductivity at a rather elevated temperature, actually. So this is sort of the landscape we want to explore. The second point I want to make is that in strongly correlated materials, we have to think of excitations, both in terms of particles and in terms of waves. So these materials really embody the fundamental duality of quantum mechanics. And let me explain this a little bit more. If we think of high energy excitations, they are best described as atomic transition. We have an atomic shell, and we add or we remove an electron. In the solid state context, these excitations, which would be sharp in the atomic system, become broadened, and they are the famous Hubbard bands. But they are best described as localized excitations and very important in multi-insulators. If we move now to low energy in metals, then we have another kind of emergent excitation that appears, namely quasi-particles, that you can think of as some sort of dressed Bloch wave that propagates over the whole solid, in contrast to the perfect Bloch wave of non-interacting electrons. Those have a finite lifetime, so they are damped. But these excitations are much better thought of in terms of waves. And the whole point of DMFT is actually to start from the atoms, to not describe the solid just as an electron gas, but really start from the atoms. Each atom is a small many-body problem in itself that we need to solve. It has all sorts of many-body eigenstates, what we call the atomic multiplets. And starting from the atoms, we want to describe the process by which quasi-particles eventually emerge as you follow the flow from high energy to low energy. So the atoms talk to each other, the electrons hop around, and eventually at low energy, wave-like quasi-particles emerge. This is actually very vividly seen in experiment. This is a photoemission spectrum of two materials, a multi-insulator, yttrium TiO3, and a correlated metal, strontium BO3. And in this photoemission spectrum, which you can think of as here it's angular integrated, so it's the total density of states for electron removal excitations. Here you see that the system has a gap. It's an insulator. But the excitation here is very simple to understand in terms of an atomic transition by which you remove an electron from the D shell of titanium in this material. That would be a sharp excitation in the isolated atom, but it becomes broadened in the solid. So that's what's called the lower Hubbard band. Interestingly, in a correlated metal like strontium BO3, this excitation also exists. And here there is a lower Hubbard band, which is hard to describe within conventional band structure theory, but very easy to understand in terms of atomic excitation. But of course, because the system is a metal, there are also quasi-particle states. These form this low energy density of states here. And these quasi-particles, if you compare the bandwidth of these quasi-particle states to the bandwidth that you would obtain, this is the dotted line, in a, say, DFT LDA calculation, for example, you see that this bandwidth is reduced by approximately a factor of 2, which means that the quasi-particle has an effective mass, which is increased by approximately a factor of 2. So this was sort of motivating remarks. And now I'm coming to dynamical mean field theory. Really, the idea of dynamical mean field theory is to start from the atoms, to describe a material as an ensemble of atoms which exchange electrons. And to do that, we're going to focus in the crystal lattice on a given atom and describe the way this atom exchanges electrons with the rest of the system as an atom coupled to an effective medium with which it exchanges electrons. So this is the meaning of the cartoon on the right here. Of course, because the effective medium is nothing else than the rest of the system, there has to be a self-consistency condition which relates this effective medium to the system itself. And here on this slide, you have the cartoon of the basic concept behind dynamical mean field theory, the precise equations that describe this embedding, this self-consistent embedding of an atom in an effective medium, and the dynamical mean field theory equations were elaborated more or less exactly 30 years ago in this paper. And these dynamical mean field theory equations become exact in a formal limit that inspired us to elaborate this dynamical mean field theory equation, namely the limit of infinite lattice connectivity or infinite dimensions that was put forward in a pioneering paper by Metzner and Volhard a little before. So the concept behind dynamical mean field theory is really that of an embedding, a self-consistent embedding. We have an atom in a bath. And let me describe this concept a little bit better. So we have to focus on a specific observable, which is related to a given atom in the solid. And this observable is going to be the local Green's function. So the local Green's function amounts to create an electron, let's say at a given time, tau, on that atom, let it evolve with the Hamiltonian, and then destroy again this electron at a later time on the same site. And for those of you who know how to decompose this local Green's function on the excitation spectrum, this Green's function actually contains detailed information about excited states with either one more or one less electrons in the system. So that will be our basic observable. In any kind of approach based on a total energy functional, we have to focus on a specific observable. In classical mean field theory, that would be the local magnetization. In density functional theory, that would be the local charge density. Here it is the local Green's function. And in order to represent this local Green's function, we are going to consider an atom coupled to an effective medium, exchanging electrons with this effective medium, and the process of exchanging electron will be entirely encoded in a function delta of tau, which describes the process of an electron hopping into the bath at time tau and another electron hopping back at time tau prime. This function we call the hybridization function because it hybridizes the atom with the bath, or the dynamical mean field. This is really the quantum generalization of the static Weiss field in statistical mechanics. The Weiss field would be a number. Here we have a full function of time or energy, hence the name D in DMFT. And at this point, this is really a representative system. We imagine we know G, and we represent G as an embedded atom, provided we adjust properly the dynamical mean field delta. So we haven't made at this stage any particular approximation. Now the approximation comes in this slide, and the organizing principle behind the approximation we're going to make is locality. We are going to assume, and let me do this here in the simplest case, namely the single band model. We are going to assume that what's called the self-energy, which relates the Green's function of the interacting system to the Green's function of the non-interacting system, is a local quantity. Namely, it doesn't depend on momentum, or if you want in real space, it is purely existing on the given site. It's local in space. And we're going to declare that this self-energy being local in space actually coincides with the self-energy of this embedded atom problem, which we also call a quantum impurity problem, because you can think of an atom as an impurity embedded in this bath. So this locality approximation is, of course, not always going to be accurate. And you can ask, when is it a good approximation? Well, from an intuitive point of view, you can well imagine that this is going to be a good approximation when spatial correlations of any kind, charge, spin, and so on, decay fast in space. So this is why I put forward this principle of locality. So when correlation lengths are typically small, which is a situation you will find like high temperature, high doping, when there is strong frustration, when you are far from a phase transition, then this will, we can expect this to be a reasonable approximation. So imposing that the self-energy of the embedded atom coincides with the self-energy of the lattice gives us an additional equation, which is the self-consistency condition of dynamical mean field theory, which can be written in this way. So it involves an integral over momentum, and it involves the knowledge of the band Hamiltonian of our problem, so the one particle Hamiltonian in the absence of interactions. We need, this is just the Dyson equation. In fact, this is directly related to the self-energy of the problem. And you see that this gives us an additional equation that relates the local Green's function to the dynamical mean field or hybridization function delta. As a result, the set of DMFT equation is really an iterative process. We have to start with the delta, solve this embedded atom or quantum impurity problem to obtain a local Green's function. And then we have to make sure that delta and G are related by the equation I just wrote. So we have two functions and we have two equations. One of these equations, this one, the self-consistency condition, is quite an explicit equation, which relates delta and G at each given frequency. But the other equation is a rather complex problem. This is a real many-body problem of solving an atom in an embedded medium. So I'm going to say a few words later on how we actually solve this problem. But at this stage, what I want to say is that once you've solved this problem iteratively and converge to the solution, you can obtain a whole range of information on the system. You will know the self-energy of the problem in this local approximation. You can also calculate higher order correlation functions, the so-called vertex functions, and from them reconstruct using both the Dyson equation and the Bethe-Salpeter equation, reconstruct single particle Green's functions for the full solid. You see that there is here momentum dependence. This is the Green's function of the full solid. And similarly, momentum and frequency dependent response functions, like the spin response function or the charge response function or the pair correlations and so on. So at the conceptual level, dynamical mean field theory share a lot of commonality with other theories based on a total energy functional and the choice of an observable. If you think of mean field theory in classical statistical mechanics, the local observable is the local magnetization. We have an equivalent representative system, which is a spin in an effective field, the Weiss field, engineered to represent the magnetization M. And we have a total energy function. In DFT, similarly, we have the local charge density. The equivalent system, the representative system, is electrons in an effective cone-sham potential. And in DMFT, our local observable is the local Green's function. Our representative system is a quantum impurity model. So in contrast to DFT, this is an interacting system. And the generalized Weiss field is a function of the energy. This is through this dependence of the energy that you're going to be able to describe both the high energy excitations, atomic-like, and the low energy excitations, the quasi-particles, wave-like excitation. So I mentioned some physical limits in which we can expect this approximation to be exact, to be good, but there are also limits in which this approximation is actually exact and controlled. And it's really important to mention these limits. First of all, there is the limit of the non-interacting system. If there are no approximations, there is no self-energy, sigma is 0, and nothing is more local than just uniformly 0 all over the Brillouin zone. So obviously, we're not making an approximation here. We describe the non-interaction system exactly. For isolated atoms, if there is no hopping, then obviously we are just describing an isolated atom, and our problem is to solve the many-body isolated atom. So we're going to have all the atomic multiplets correctly. So the theory is also correct in the atomic limit, just because our assumption that the self-energy is local is obviously correct when there is no hopping. So this is a key aspect of the theory, that it provides an interpolation from weak to strong coupling. Very importantly, and this was at the root of the elaboration of this dynamical mean field theory equation, the theory is also correct, is also exact in the formal limit of infinite dimensionality. And this is because the non-local components of the self-energies are down by higher powers of the inverse connectivity of the lattice. So this is sort of the general conceptual framework. Let me now move a little bit more into some of the results, and I'm going to of the applications, and I'm going to start with a very early success of DMFT, which is already several decades old, which is that it provided us with a theory of the mode transition. So this is just a cartoon where I'm thinking about a system in which we increase the interaction strength. So we have, let's say, integer number of particles per site. Let's say we have a Hubbard model with one particle per site and some frustration of the magnetic order as a function of temperature and interaction strength. We can have a transition in this system between a metal and a mode insulator. The mode insulator being a state of matter that I already alluded to for V2O3, in which the particles are localized because of the strong Coulomb repulsion. They just cannot hop like being blocked in a subway because there are too many people in the subway car. So the electrons are blocked, and we want to describe this transition from metal to mode insulator and the various crossovers associated to that. So by solving the dynamical mean field theory equations, we actually can get to a full, consistent description of this transition. And when we look at the, say, photoemission spectrum or the local spectral function as a function of interaction strength, the calculations reveal an evolution of that type, where our original density of states, here represented with 1 electron per site, this is the occupied part here, evolves as a function of interaction strength. And you see that the lower Hubbard band and upper Hubbard band appear. And at the same time, the low energy density of states here has a bandwidth which is increasingly reduced as we increase interaction strength, which reflects the increase of the effective mass of the system. At some critical value of U, which is here, the quasi-particles completely disappear, and we open a mode gap, and we have a mode insulator. So this was one of the early success of the mode transition. It allowed to be applied to a number of systems and a number of models. This is actually a concrete calculation now, not a cartoon, for the optical conductivity of the Hubbard model. And what you see here is how the optical conductivity evolves from the low temperature regime, which is this black curve here, which has a Drude peak, a characteristic feature associated with the Landau Fermi liquid regime of the quasi-particles, and transitions to the lower Hubbard band. And as you increase temperature, what you see is that there are transfers of spectral weight between these various features. And I know Gabi will come back in his talk on these questions of transfers of spectral weight, which is really an important feature of strongly correlated systems. So at this stage, I cannot resist quoting a sentence from Phil Anderson, who about 20 years ago, after the successes of DMFT describing the mode theory, wrote that after nearly 50 years, thanks to DMFT, we finally are able to understand the mode transition, at least in higher inner dimensions, and to model the Kondo volume collapse in cerium. And 20 years later, now we could add to this list many, many things that DMFT has provided to the field of strongly correlated electrons. So to just give you a little bit of a broad brush idea of how the theory has evolved, I like to represent it a little bit like a tree. So this is my idea of a tree with my poor and limited talents as a graphic designer. So here is the trunk of the tree. This is the conceptual core of DMFT. These are the basic DMFT equation, the concept of a self-consistently embedded atom in a bath. So this is what I described briefly in the previous part of the talk. And of course, in order to make this a reality, we have to be strongly rooted in various algorithms that are used to solve this quantum impurity problem, what we call impurity solvers or DMFT solvers. And there are many, many types. I will come back a little bit on this, but there are quantum Monte Carlo methods, methods based on the Wilson numerical normalization group or tensor network, the emerging methods, quantum chemistry types of methods like CI, approximate solvers of various types. All these under the hood development of algorithms to solve the DMFT equation is a very, very important activity in the field, which is started from the very beginning and is continuing very actively today. And then there are many applications of DMFT to a number of systems. They can be models like Mott-Hubbard models, Kunz multi-orbital models, Kondo lattices, and so on. And of course, also, and Gabi will elaborate a lot more about this in his lecture, applications to materials, combining DMFT with electronic structure, and application to a number of systems, oxides, rare earth, actinides, organic materials, and so on. And then here in the upper part of the tree, I've tried to give you a glimpse of the various extensions of the theory, because for certain systems, we need to go beyond the local approximation, or we need to go beyond equilibrium. We need to extend DMFT in various directions. And this has been done along different directions, for example, extending towards non-locality with cluster embeddings, calculating higher order correlation functions and response function, and using these response functions to go beyond the locality approximation, or extending DMFT towards non-equilibrium systems. And by now, there are a number of review articles that cover all these various roads and branches and conceptual core of this tree. So on this slide, I've tried to give you, to indicate quite a number of review articles that have appeared over the years, certain very recently, which actually detail these various methods and these various extensions. Okay, so as I mentioned, under the hood, in order to make this theory practical, there is a very active effort. There's been over the years a very active effort of developing efficient impurity solvers. And this is really a crucial activity in the field. There are various kinds of solvers, solvers working with a continuous bath, typically quantum Monte Carlo, solvers requiring a discretization of the bath, like exact diagonalization methods or Wilson numerical normalization group. And by now, there are a number of softwares which are available on the web that allow you to solve the dynamical mean field theory equations and also to apply the dynamical mean field theory equations combined with electronic structure methods to study real material. And I'm not sure this list is fully exhaustive. I hope I didn't forget too many important codes, but you see here that there is really an ecosystem of these codes that makes for a very lively community. One of the important breakthroughs in the field of these impurity solvers has been the elaboration of quantum Monte Carlo algorithms in continuous time of various types. I don't have time to enter into the details, but these algorithms are really the workhorse of many of the applications of the system today. So I briefly mentioned the fact that there's been a happy marriage of DMFT with electronic structure based on either DFT or GW methods. This has been a real interdisciplinary and collective effort, which started about 20 years ago and is still continuing today, and which allows to apply the DMFT framework and DMFT equations, not only to simple models, but also to real materials with their structural and chemical complexity. I think Gabi in his lecture will describe how this works in more details. The general picture about this is that we have to clone together the electronic structure world and the DMFT world. This is done by, for example, if you use DFT, by solving the Kohn-Sham equations, defining the target of states in which we're going to apply a restricted Hilbert space, say the shell of a given atom, which we can construct by constructing Vanier functions, for example, for a restricted set of states, and applying the MFT many-body self-energies to this subpart of the Hilbert space. We have here the DMFT iterative loop, at the end of which we can recalculate the total charge density and update the electronic structure part, so as to finally reach convergence on both the self-energy, Green's function, and local charge density in a framework that unifies electronic structure calculations and DMFT. And this has been applied to many materials with F electron, D electrons, organics, and so on and so forth.
And Antoine,
one thing also, yes,
I had promised to give you a 30 minutes ping.
Thank you. So noted. So one thing I want to say, and this is a really important thing to emphasize when it comes to applying the dynamical mean-field theory ansatz to the real material context with multiband and multi-orbitals, is that what we mean by the locality assumption has to be taken with a grain of salt. What we really mean is that when we express the self-energy of the problem in the set of localized orbitals, which defines our correlated sub-Hilbert space, the self-energy is assumed to be a k-independent function. It's a matrix in the orbital indices, which depends only on energy. But of course, when we upfold that self-energy to the whole solid and re-express this self-energy in the block bands or in the quasi-particle states, then this becomes an object which depends both on momentum and energy, because the orbital composition of the block states or the quasi-particles for a given band depend on k point. So these matrix elements that sort of relate the block space and the Vanier or the localized orbital space may be very strongly k-dependent, especially if there is spin-orbit coupling, for example. And the embedding assumption, which is behind the MFT, is really expressed by this equation. It's really expressing that in the orbital space, the self-energy is really only frequency dependent. So can we put this equation to the test from experiment? Can we actually, on a given material, test whether this ansatz here, locality in orbital space, is a good answer? So this is something that we've done recently with colleagues in Geneva, Anna Tamay, Felix Baumberger, and their group, on a material, strontium 2 ruthenium 4, which is really sort of the Drosophila of transition metal oxides. It is a system which is so pure, in which you can synthesize so pure crystals that many of the standard experimental methods in the toolbox of condensed matter experimentalists can be performed, basically all of them. It's a system that has 4 electrons in a T2G shell of the ruthenium atom. And it has, because it is a T2G shell with 3 orbitals, the Fermi surface has 3 sheets. And here what you see is that the orbital composition, which is color-coded here on the different Fermi surface sheets, depends very strongly on angle. So this is the dependence on angle of these matrix elements. And what we did in this paper is actually to take the photoemission data along the different angles around the Fermi surface. So here you see the very beautiful experiments by Felix Anna and co-workers, in which you can follow the dispersion of the quasi-particles. And just with your naked eye, you will observe that the way these quasi-particles disperse is actually depending on angle. It's not local in K, it actually does depend on angle. But the point is that this we could show by extracting the self-energy in the band basis and in the orbital basis directly from the experiments, that this angular dependence is entirely encoded in these matrix elements here, while when expressed in orbital space, the self-energy we can extract from the RPS data is actually very weakly momentum dependent. And this is what this plot here demonstrates, namely that all the self-energy determined from the different angular sectors in this material can be collapsed on basically two curves corresponding to one self-energy for the XZ-YZ orbital and one self-energy for the XY orbital. So this is a vivid demonstration that in a material which is a layered 2D material with a certain amount of spin fluctuations, so correlation length, which at low temperature is about 3 unit cells, nonetheless, the locality assumption is actually a good assumption when you express it in the proper basis. And this is a comparison between a full DFT plus DMFT calculation, the plane lines for the self-energy and the experimental data, and a similar comparison between the color map here, which is the color map of the spectral function from DMFT, and the white circles here, which are the measured dispersion of the quasi-particles from the experiment. So this is an illustration of how powerful the theory is when applied to a concrete material. In fact, as I'm sure Gabi will explain in this talk, this material is a member of a big and happy family, which is the family of Hund metals that also contains the iron superconductors, for example, and many of the 4D transition metal oxides. One of the very, very interesting aspects of these materials is that the typical scale at which the orbital and spin degrees of freedom of the atoms are getting quenched is distinct one from the other. So there is a very interesting flow in this system from the high temperature regime where you have where you have localized atomic-like excitations described in the particle language, down to the low energy regime where you have emergent quasi-particle excitations, which is the one I just showed from the photo emission data a moment ago. So if you want, the way we think about this system in DMFT in the cartoonesque way is that we have a bunch of atoms in the crystal lattice. Each of these atoms here has 3 orbitals. These are the 3 quadrants. The many-body problem of each atom is already a rather complex many-body problem. If you solve this atom in this 3-orbital shell with Hund and the on-site U, you will find that the ground state is 9-fold degenerate. And when you actually have electrons hopping around in the crystal lattice, this degeneracy is gradually lifted. At very low energy, we reach the regime where there are quasi-particles. And this is really how we think of the system in dynamical mean field. At high energy, we have atomic configurations and multiplets with fluctuating entities, particle-like excitations. As we flow down to low energy, we have quasi-particles that emerge, and eventually collective ground states with symmetry breaking. So this brings me to the last minutes of the talk, in which we need to cope with the question that as we go down in energy, the correlation length for this incipient symmetry breaking and ordering is going to grow. And at some point, the dynamical mean field approximation may not be enough to actually decide where the system wants to go and what is the physics in the very low energy range. So obviously, this calls for a framework to include spatial correlations beyond single-site DMFT. So at very high energy, we have atoms. At low energy, spatial correlations grow, and we have to go beyond single-side DMFT. Single-side DMFT can predict the ordered phases, but it will predict it in a mean field manner. So there are many routes to do that. They go under the name of cluster extensions of DMFT or various extensions of DMFT based on non-local, including non-local correlations to higher order correlation functions, or extended DMFT, GW plus DMFT. Let me briefly give you an idea of how cluster extensions of DMFT work, and then I will conclude the talk. So one of the versions of cluster extensions of DMFT, the so-called dynamical cluster approximation, but there are others like the cellular DMFT, amounts to partition the Brillouin zone into little pieces like this and assume a self-energy which is no longer constant over the whole Brillouin zone, but actually piecewise constant. So it's a discretization of the self-energy through the Brillouin zone. And this has been developed by many, many groups in the world and very successfully applied to, for example, the DOPE 2D Hubbard model, and established this, one of the claims to fame of these approaches is that, in my view, it has now established that the 2D Hubbard model has a pseudogap, and that this pseudogap is entirely caused by spin correlations, not by other types of correlation. And now, actually, there's been a handshake of these approaches, which I think with other approaches that really establish these conclusions on a firm and solid basis. Okay, so I'm going to have to skip a few slides just to flash a conclusion. So basically, looking ahead, we have this theory. It has been applied, and it's being applied to many different materials. Non-local extensions are being developed. What do we want more? Well, we need still more progress on impurity solvers to handle more orbitals, to do a better job on real frequencies at low energy, and so on. And there are promising candidates. We need to push the methods of integrating DMFT with electronic structure, in particular, including long-range interactions, and GW plus DMFT is a promising route for this. And we can think of new embedding schemes. They come with various names, DMFT being sort of the poster child. I think a very interesting direction is that there is now a handshake between other types of computational many-body methods, especially the ones that start more from ground state wave function and use entanglement as an organizing principle, and the ones like DMFT, which start more from the high energy side and use locality as an organizing principle. And one very interesting development in the field is that these two types of approach are now talking to each other to establish things in this intermediate region where things are difficult. Thank you very much. Let me just flash a few references. So 1996 review articles, some very interesting and nice collections of lecture notes published by Eva Pavarini at Jülich, and my Collège de France lectures devoted to DMFT in 2019 for additional references.
Great, thank you, Antoine. This was beautiful and very helpful at all levels. There is the question and answers pane. So what we'll do is that people are very welcome to write their questions in there, and I'll ask them, or you can go live and answer. But maybe let me get started. And in some ways, you often have, refer to these principles of locality. You've talked about localized electrons, high energy excitations. How do you see, the approach when it becomes a bit less clear what is, the localized impurity that you want to solve? Or is that ever a case? Because after all, atoms in solids are still atoms, and so the approximation is very good. But do you see a limit in somehow the strong correlation becoming a little bit difficult to pin down in terms of space?
So perhaps there are two sides to your question, Nicola. One is how do we go from the regimes where the excitations are well described in terms of localized excitations down to the low energy regime where we have obviously in metals very delocalized quasi-particular excitations. So that is precisely what DMFT aims at doing. But I think and I think does successfully, but I think your question is actually more about do we have systems in which identifying the subspace that we're going to treat with many body methods like DMFT is not so obvious, right? Yeah. Yeah. Okay. So I would say that, let me think a little bit like a quantum chemist. Okay. When we handle the system in the right basis, we are going to be able to identify orbitals that are completely filled, orbitals that are completely empty, and orbitals which are partially empty, partially filled, right? And usually these are the ones which are, I think the quantum chemists call them the active orbitals. So analyzing this in this term allows usually to identify the active orbitals, which are the ones that demand a many-body treatment.
So it's almost
now, of course, there is. Yes, go ahead.
No, so it's almost an energy criterion. It becomes rather than a localization.
Yes. It's an energy criterion indeed, and there's been, of course, very interesting directions to actually do full cell embeddings in which you retain on the embedded atom many more orbitals than what we do in more downfolded approaches. Garnet Chen and Tianyu Zhu at Caltech and Yale have been pushing this very hard. And I think this is very interesting. At the end of the day, this analysis in terms of occupancies plays a role in this full cell embedding and allows to identify the active orbital.
Thanks. So let me actually call up questions from the Q&A. We have one from Marco Grioni. I don't know. Yes, we can have it live. Actually, Marco, you'd be very welcome to ask. And then maybe another one from Lenka Zbederova that we can also go live. Thank you, Marco.
All right. Thank you. Can you hear me?
Very well.
Yes, Marco. Great to see you again.
Hello. Great to see you, and thank you very much for the beautiful talk. I had the impression that I could understand something, but you know, you're never sure. So my question is, how does the interaction between the electronic quasiparticles and collective excitations like phonons and magnons fit into this framework?
Okay. Excellent question. I'm not sure I'm going to have time to really answer that question satisfactorily. So the collective excitations. So let me separate electronic excitations and phonon excitations. The calculations of forces and phonons in DMFT is something that has been done, which is still being actively developed. The Rutgers group and Christian Haule in particular have been very active on this, and also Ivan Leonov. But this is something I know a little bit less firsthand, so I will mostly comment on the electronic excitations. The electronic excitations can be, their dispersion can be, the collective modes can be calculated within dynamical mean field theory. However, the feedback, the key question, and your question is very much to the point, the key question is the feedback of this collective mode, let's say magnons, for example, into the physics of quasi-particles. And this feedback is really the thing which is missing in the single-side DMFT approximation. And it has been the motivation for these extensions of DMFT that precisely try to, and often successfully, describe the feedback of the collective modes on the quasi-particle. So in technical terms, the self-energy in these approaches is typically represented as a local part plus a non-local part which comes from, let's say, for example, the first few diagrammatic contributions which describe the feedback of a collective mode into the physics of single particle excitations. So this is beyond single side DMFT, and approximations like D gamma A, free legs, dual fermions, dual bosons, and so on have done that.
Thank you.
Thank you, Antoine. Maybe we can go live with another question from Lenka Zdeberova. I think, yeah, great. Lenka, please.
Hi, do you hear me?
Yes, very well.
Yes, hello, Lenka.
Okay, thank you. Hello, Anton. Thank you for the very nice overview. It was really nice. And my question is about avenue for DMFT that I have been thinking a lot these last days. That is where DMFT can potentially also play a very important role is in the analysis of algorithms that are actually used to train artificial neural networks and in all that business of machine learning. So contrary to what you are mainly describing, these are classical systems, and they in a sense live in infinite dimension, not embedded in finite dimension. So that should make them simple. But the interactions between the degrees of freedom there are through the data that act as a disorder, and that kind of complicates the things. And I just wanted to have your generic thoughts about what do you think that people trying to use DMFT in that business of neural networks should learn from the studies of strongly interacting electronic systems, and should we kind of talk more? I would like to kind of understand more of what has been done. It seems a bit difficult. How should we go about it?
Okay, well, not exactly an easy question, Lenka, and I find it a very interesting question because at a certain level it comes full circle. What I mean by that is that the ideas that, and maybe we'll talk about this more in the fireside discussion later, the ideas that led to DMFT have their roots, at least that's what I think, and I'm sure Gabi shares this view, in statistical mechanics idea to a large extent. And, you know, it's no random fact that both Gabi and I have a past culture in spin glass theory and stat mech theory, which led us to these things. So we were inspired by statistical mechanics to develop this approach. So now you are sort of asking the full circle question, can one get inspiration from what has been done in the quantum world to understand better the sort of dynamical mean field equations of the stat mech problem that you described? What do I have to say about this? There are certainly some commonalities, right? I mean, the solution of a time-dependent problem coupled to an environment is the sort of thing you're going to have to face and has been faced in the field of the dynamics of spin glasses, also of ecosystems. Direct inspiration from the quantum many-body world, I'm not so sure, but I'm afraid I'm not going to be able to answer. I mean, that would be more like a discussion we need to have next time. I believe.
Okay, fair enough.
But I'm sure there are interesting things to learn, because the conceptual framework of DMFT is to a large extent inspired from statistical mechanics.
No, very fascinating. I wonder when our neural network will go paramagnetic. But thanks, Lenka. And maybe one.
It's easy, Nicola. That's when they don't learn anything.
Yeah.
I always wanted to write a paper called Death as a Phase Transition, and I think that's exactly when you stop. A quick question, and then I will go for a break. Antoine, you have presented today's lecture very much in a constructive fashion. So you build things, you separate the degrees of freedom and you create this embedding theory. What about a deductive approach? That is, you write a functional and you derive it. Do you also see it in sort of that perspective?
Yes, the whole theory, especially when you combine DMFT and electronic structure for real materials, can be built as a total energy functional. So I don't know if Gabi will explain this in this lecture, but this is something which is very dear to our heart. You have to start with identifying what your observables are going to be, and for a real solid, they're going to be the total charge density and the Green's function projected on a specific subspace. So these two entities are linearly independent. You cannot calculate the Green's function just from charge density, but if you only know the projected Green's function on a restricted subspace, you also cannot reconstruct the full charge density. So it's legitimate to construct a functional in terms of these two objects, right? And you can actually write down an energy functional, which is involving these two quantities, which is the DFT plus DMFT energy functional. You can do similar things with, if you start more from the GW perspective, where you are going to write a function of G and W and derive all the equations of the theory from this perspective. I don't know if this is answering your question.
I think yeah, thanks. It's a great cue-in also for the talk of Gabi, and it gives us the direction. I would say, I would continue forever, but I think it's also good to give ourselves a brief pause just to make sure that, we keep up ourselves the attention. So it's a time for a coffee, herbal tea, or a shot of whiskey, depending on your time zone. And we'll stop for 8 minutes and we'll start again. It would be 4:10 European local time. But in the meanwhile, we thank again Antoine for your very inspiring talk. And we'll listen to Gabi and then we'll join together. Great. So welcome back, everyone, for our second talk in the second Marvel Classics on molecular materials modeling, dedicated to dynamical mean field theory. And so also a very, very great pleasure for me.
Unable to start video. The host has started my video.
Okay. So
you can start your video because the host has stopped it.
No, it's good, Gabi. We are seeing you, we are hearing you. So it's all, you are live.
Okay. Okay. So then let me then see if it's possible to share the screen or whether this.
In the meanwhile, I'll just do a brief introductions. Again, no need of introduction, but just to give a little bit, maybe the sort of biography. You did your PhD in Princeton University, moved as a postdoc to Santa Barbara, and then assistant professor at MIT, and then ever since at Rutgers University with a board of governors chair, currently directing the Center of Theoretical Spectroscopy and Materials Design at Brookhaven National Library Laboratories, and the director for the Center of Materials Theory at Rutgers. Of course, interest lifelong in strongly correlated electrons, superconductivity, prediction of D-wave superconductivity, pseudo gap, and in general strongly correlated materials. Also, a recipient of the Agilent Europhysics Prize in 2006, the Anizur Rahman Prize from the American Physical Society, and the Feinberg medal, all for dynamical mean field theory, besides many appointments, including in particular the National Academy of Science and the American Academy of Art and Science. I think we're all good to go, Gabi, for you. Okay. Would you like a note after 30 minutes, or I let you?
Yes, that would be very useful.
So I'll interrupt, and again, the floor is yours, and many thanks again for contributing.
Can you see my screen and my full screen?
It's all good, yeah.
Okay, very good. So thanks very much for this opportunity to speak here. It's a pleasure to have a friendly discussion about things in this forum. So thank you very much. And also, like Antoine, I really would like to thank all the people with whom I learned about strongly correlated materials through the years. And there are too many to go through, but I made an effort to acknowledge both people who are not here anymore, or as well as students and postdocs. And there's so many, and I apologize to those whose name I forgot. So following Antoine's talk, what I thought we would do here is go through some of the same themes, but maybe with a more materials-oriented perspective. So what I'm going to do, and let's see if I can get maybe my laser pointer here, which would be good to have. Laser pointer. Yes, I have laser pointer. Can you see my laser pointer?
Yes, all good.
Okay, good. Good. So in the first part, I would like to say a few things about DMFT, just to establish a little bit of continuity with what Antoine said. But then what I would like to do in the rest of the talk is just give you some flavor of the excitement that generates understanding materials. So I'll go through what I call the different roads to strongly correlated behavior, the different types of correlated electron materials, what MOT does, what the heavy fermions is like, the Hundsness, what type of physics there is in the actinides, etc. In a way that if I don't get to the end of this, it doesn't matter, because you will get a flavor of why it's so exciting to develop and to use dynamic mean field theory. And then I hope that we have like a minute or so to discuss future directions, and that can also be the subject of the fire chat talk. Okay, so let's start from the very beginning. I mean, we owe a lot to those who developed the theory of weakly correlated materials. And this goes to Landau, and this goes to Kohn and Sham and Hohenberg, because what they did is they somehow managed to give us a reference system which we can use to think about materials. And from different perspectives, what they show that in some sense, for many properties, we can visualize the material in terms of bands, which live in K-space, and where the interactions have, in some sense, disappear. Landau does that via a renormalization procedure. He says that eventually at low energies, the interactions renormalize to zero, and therefore we can think in terms of electrons without interactions. The density functional theory postulates or derives a system which produces the exact density of the solid, and then it turns out that in many materials, this Kohn-Sham spectra is a good starting point for adding Coulomb interactions in perturbation theory. That's what's called the GW method, and that gives us a good approximation to the spectra of correlated materials. So these Kohn-Sham quasiparticles are good to start to do perturbation theory and get the physics of weakly correlated materials. And just to pay my respects to those founders, I just show an old slide from Stephen Louis in which he shows, well, there is great deal of predicted power in this. And this is on an old slide. It's a G0W0, and it has been perfected through the years, but it's clear that over many semiconductors, the LDA underestimates the gap, and then comes the G0W0 and gives you something which is not so far from the experiments. So, and many other things can be constructed. And sort of the dream behind all this dynamic mean field theory and extensions to deal with real materials is to be able to do something so good and so predictive as our forefathers have done for the weakly correlated systems. However, in order to do that, we will have to strongly modify this reference system, because a better reference system for the correlated electron system are atoms, like Antoine explained, rather than bands. And in fact, I would say you need to do both. You need to have a framework which both has bands and both has atoms. And that's what dynamical mean-field theory does, which is what Antoine explained. So that's sort of the foundation. And a little bit about the history. I mean, so far, the field of correlated electron systems is just a history of unexpected discoveries. Just nobody expected electron-driven metal-insular transitions in the 1960s, because band theory says that things whether it's even or odd number of electrons with an odd number of electrons have to be metals, and with degenerate bands have to be metals. Again, nobody expected that we would see quasi-particles with masses with 1,000 times the mass of the electrons at low temperatures. Nobody expected that an oxide would be a superconductor, and there are many, many, many other things. Nobody expected that there will be superconductivity in an iron-based system at high temperatures, and more recently, nobody expected a nickel version of that. So it's a history, and I bring this just to give people the flavor. I mean, this was a field that was entirely driven by surprising experimental discoveries, and the theorists were running behind trying to explain the experimental discoveries. And what's exciting for me is that dynamical mean-field theory now is evening out a little bit the playing field, in the sense that now theorists can actually compete and can think on equal footing about what can be interesting. We will not always get it right, but at least we have some tools to enter this fantastic playground, because there are lots of new things to be discovered in this field. And I also would like to say that these days, I think a little bit more broadly about correlations as opportunities in material research, where I think quantum embedding methods can be of use in materials which are not so strongly correlated. So I think that the field has moved, and dynamical mean-field theory has given it a lot. Okay, so this is the basic problem. I mean, we know what atoms do because atomic physics is a closed field. We know what bands do because we can do GW and perturbative approaches around it, and we can get weakly correlated materials. But if you're not in either one limit, what do we do? And as Antoine explained, now we have something we can try, and it's dynamical mean-field theory and the extensions. So this is sort of the only slide I have to explain dynamical mean-field theory. But since there are students in the audience, I would like to try that. But this slide is just to convince you that if you know a little bit of statistical mechanics and a little bit of many-body theory, you can invent dynamical mean-field theory for yourself and get the dynamical mean-field equations right. Because the thinking is extremely simple. And like any mean-field theory, you start with a lattice model. You start with something which has many degrees of freedom. And like any mean-field theory, what you want to do is you want to reduce this many-body problem to a single-side problem embedded in a medium. So let's see. So that's my cartoon of the embedding. And in the Ising model, the many-body problem is the Ising model that you know very well. And how do you get the mean field Hamiltonian? Well, you sit at one side, you look at the spin, and you ask, what are my neighbors doing to me? And you say, well, my neighbors are acting like an effective field. So let's do exactly that reasoning for the Hubbard model, which is here. Now we have electrons. These are quantum mechanical operators, or Grassmann variables, and they're moving in a lattice, and they have an on-site interaction U. And now let's just select a site, which I call 0, and let's ask, what's the action for that site? Well, first of all, you need to have the atomic action. You have dd tau plus mu. You have the U. Everything which is local on the U site, you keep, okay? And then the only thing which was connecting the different sites is the hopping. So what are we going to replace the hopping? Well, just like here, we sort of think about what happens if you integrate out all the other degrees of freedom. The simplest thing you can get is just what's called the hybridization, which is non-local in time. So that's basically how you get the impurity model. And here I'm using a Lagrangian formulation, but I could have done a Hamiltonian formulation. The idea is simple. So you see, the analogous thing to the Weiss field is now the function, which replaces the kinetic energy in a local description of the solid. And it tells us the ability of the electron to move, and of course is non-local in time because I integrated out quantum variables. So this is clear what it has to be. Now the question is, how do we figure out what delta of omega is? Well, we follow the thing you already know. Once you have your local problem, you have your Weiss field, and you can compute all local observables, in this case, the magnetization. So here we do the same. We have the impurity model. We can compute the local Green's function, which I call G, which is a functional of the hybridization. And then we need to close the equations. We need to sort of say how we're going to determine our effective field. And that involves, of course, the things which are the non-local, the thing that connect the different sites, the Jij. Well, the analogous thing of the Jijs are the Tijs. And this equation, you just guess that the Weiss field that each neighbor produces is J times its magnetization plus the original magnetic field. And here you also reason by analogy. I have this impurity here, I have this impurity model. And then with the impurity model, I can compute a local self-energy, and I compute, which is a functional of delta, and I can compute a local Green's function. And now this is my lattice Green's function because I know the self-energy, and these two things have to be self-consistent. So the local Green's function is obtained by summing over K. So that's the DMFT equation, is a functional equation for delta. So it's exact in the very important limit that was introduced by the pioneering paper of Metzer and Folhard. And the only real difference between the Ising model and the dynamical mean-field theory is the time, the additional variable, and the level of difficulty in solving the quantum impurity model. And Antoine has discussed that, and I'm not going to go over this. I just want to leave you with the idea. And then now let's sort of move more towards realistic systems. That will be my job in this talk. So we want to start from crystal structure and atomic positions, or we even would like to figure out what should be the crystal structure and atomic positions. And then basically we would like to compute observables, things which are useful. I mean, the things that experimentalists measure. And there are really two paths. One way is just to go really directly ab initio, and the other way is trying to derive some simplified models and then proceed from the model Hamiltonian. And dynamical mean-field theory works in both cases in different ways. And for doing material science, we need both, and we'll see that in the talk. And this is something that we should discuss, why it's really important to have this, but it's also really important to have that. And my job here will be mostly explaining why we need this and why it's exciting to have that. Okay, so now we're transitioning from the DMFT for models to realistic things. And sort of like Antoine explained, we have an impurity model, and from the impurity model, we can generate local quantities from the local such as the self-energy or the irreducible blocks of correlation functions. And then from there, we can compute the things that people measure in neutrons, susceptibilities, in photoemission, in ARPES, the Gs. And okay, that's basically can be done very well in models. The transition to the realistic system is that now we take a leap of faith. Now our quantum embedding is in a much bigger space. We are only going to keep the most correlated shells, the most correlated atoms. Everything else we treat like we treat in DFT with an average potential. So it's a much bigger embedding, and that's where the choices of projectors and embedders become much more crucial. It's a big leap of faith. And then we need the effective parameters for those shells, for which we have some methods. And this leap of faith was done after some successes with models that encouraged that. And it was done by Lichtenstein and Katz-Nelson and by our group in collaboration with Anisimov group in Ekaterinburg. And basically, the idea is to really embed in this much bigger space. And the way to understand the LDA plus DMFT is to think first about what the DFT loop was. The DFT loop was getting a density, evaluating a Kohn-Sham potential. Then we evaluate a Kohn-Sham-Green's function. So don't look at this line. Think of putting here your Kohn-Sham-Green's function, and then your Kohn-Sham-Green's function goes back and gives you a density. So that's, you all know, that's your DFT loop. Density, Kohn-Sham potential, Kohn-Sham-Green's function, and from the Kohn-Sham-Green's function, go back to the density and iterate until you converge. That's your DFT loop. Now, Antoine explained very well the DMFT loop, so I'm not going to explain it, but he was very pedagogical and gave a beautiful presentation. We have some lattice Hamiltonian. With the lattice Hamiltonian, we know how to get local Green's functions. We know how to get the Weiss field for an impurity, and the impurity gives us a self-energy that we have to put in here. So now we get these two things to talk. So we're going to upgrade the Green's function, which is here, to something which has the two worlds, the DFT world and the DMFT world. So here, the lattice Green's function is made out of a DFT piece and a more correlated piece for the shell. And that's the thing which is new when we do DMFT plus LDA, since this Kohn-Sham potential already had the exchange correlation potential, we need to take out what's called the double counting correction to not to double count the energy. But I think this is intuitive, and this is the LDA plus DMFT loop in the way that it's implemented nowadays. And you have to say, okay, I want 20 DFT iterations and I want 15 DMFT iterations, and then see what result we get for this lattice Green's function. And I should say that, I mean, while it looks simple, there are many, many moving parts, and a lot of effort has been put by a whole community in terms of showing that something like this eventually can work. And I should stress, for example, that there are many ideas how this double counting is, in particular, one very good by my colleague, Christian Haule. And I would like also to mention that, in fact, this double loop where you iterate over density and you do the DMFT loop was not done in the first initial papers, but it's something that actually Sergei Savrasov, who came from the electronic structure community, implemented at Rutgers and implemented in some sense the first electronic structure package from Ole Anderson's LMTOs, which also had some DMFT option. So that was in the prehistory, in the beginning of this century. Now, as Antoine mentioned, there are many, 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 many electronic structure codes, and I'm sure he did a very comprehensive description of this. All I would like to mention, since I'm obliged to serve as director for a national laboratory, is that Brookhaven National Laboratories maintain ComSuite, which is a package which has very interesting features, and it's an attempt of a national lab to be a player in this field. Okay, Antoine mentioned the functionals, and I decided that I would say something about it again for the electronic structure community. And what I would like to say is that these functionals are basically functionals of the density and functionals of the local Green's function. Or just like in DFT, sometimes it's better to take more variables in the functional. Is this Harry Fulke's functional that has, for example, rho and the Constant potential. Here, sometimes you want to take more variables and you want to take the Constant potential and the local self-energy. And then basically it is essentially something that you should identify as the DFT functional, something which is like a Bain-Kadanoff functional reduced to the atomic shells you consider. And then you sum both, and then you take out the double counting correction. The beautiful thing about this is that once you have that, you can do total energies, you can do structures, you can do forces. And there are, of course, moving parts. And just like there are moving parts in DFT, I don't put this anymore as a moving part because so much has been explored about the exchange correlation potentials in DFT that it's not really a moving part because we know exactly all it does. There are many that can be used, they can be downloaded, they've been compared, you know what works for each material. There's a lot of expertise. Here we are in the prehistory, but you should know what the moving parts are. And the moving parts are how you embed this self-energy. Those are your embedders or your projectors. You should know what double counting you use. You should know how you screen the Coulomb interactions. And just like it took years to figure out optimal choices for different materials, here it will take some time until this thing is in the same shape as the DFT stuff is. But I mentioned that as a sign of respect to the DFT community and how far more the electronic structure community has to go. Okay, so I mentioned the functional. And I cannot underestimate the importance of that if we think about really doing something useful for society. For example, designing materials, comparing structures, doing molecular dynamics. For all that, we need stationarity. And that functional that I wrote, if you extremize it, gives you the DMFT, the LDA plus DMFT equations, and its extensions can be derived from there. Or phonons that are very useful, or molecular dynamics, that an area where Nicola has been very active. And all this is a very active area of research. And I would like to mention, for example, my colleague Christian Howley has been doing a lot of work in this area. Now, I'm not doing justice to this on the functional because there are many more. And there is a very deep parallel between DMFT and DFT in the sense that they both can be formulated as exact theories. In both cases, you can make approximations. And all this is discussed in a review written with colleagues. So I won't delve on this here, just mention, since it's also important, that just as an example, that one can actually think of functionals of G and W that as lowest order gives us the GW approximation, that truncated gives the GW plus DMFT by summing all the local diagrams, and that can, this is sort of the thing that is called GW plus DMFT, which I will not have time to talk about, but many approximations can be designed using functionals, and that's sort of a completely interesting field that I will not cover. So now I want to give you some idea of models and realistic stuff and the excitement of looking at materials. So here we have our beloved Haber model in one band. This is the DMFT phase diagram that Antoine already covered. And yes, when that thing was solved, one discovered that the spectral function changes in ways that the band theory cannot possibly predict. It goes from having a gap in the paramagnetic insulating phase, and in the metallic phase, there is quasi-particles and Haber bands. And all that was sort of modeled, and there were lots of qualitative ideas that came from there. And of course, we had in mind that, yes, this does look a little bit like vanadium oxide, but if I think about it in retrospect, it's almost crazy to try to apply dynamical mean field theory for the one-band Haber model to something which is as multi-orbital as vanadium oxide. But that was tried. And as I said, it was completely crazy, but this interesting physics that the model captured, that tiny changes in the temperature cause big redistributions in the spectral weight over scales of 10,000 degrees. So here we're talking about changing the temperature by 100 degrees and redistributing the spectral weight over a scale of 1 electron volt, which is 10,000 degrees. It's more than the model. It's some general feature of correlated electron materials. And we did talk to the experimentalists at Bell Labs. At that time, there was Bell Labs, and there was a Gordon Thomas, which could do optics. And he dared to measure the optical conductivity of vanadium oxide at 2 temperatures, and he observed precisely that. So there is a leap of faith in using models, but sometimes models have some universal features that transcend the model. Of course, this is no proof that this is what's going on in the material, and by now there are many, many, many real DMFT studies, and I will mention only one by a group in Rome, Massimo Capone and Baldassare, which do much more measurements, much more temperatures, but the outcome is the same. The physics of MOT is charge blocking, and when you raise the temperature, the optical conductivity goes down in a broad energy scale, because this is a MOT system. And we've been looking at it recently as well, with the goal of going even further. There are ideas about what the quasi-particles do and why this bad metal with the resistivity are very large that emerge from dynamical mean field theory, in particular work done by Antoine on resilient quasi-particles. But we thought, well, that was one bad Haber model. We can put it again to the test. And the idea that the reason why there's this weird temperature dependence in vanadium oxide is not only because the quasi-particle is temperature dependent. In fact, the quasi-particle has hidden Fermi liquid behavior. It has sort of some T-square behavior. The reason why we have this unusual large resistivity is because the effective plasma frequency at low energies is temperature dependent. And that's what happens in theory and the experiment. So this handshake between theory and experiment, I think, is key. And one of the great triumphs of dynamical mean field theory is that it facilitated this handshake with the experiment. And this paper we entitled Shining Light on Transition Metal Oxides, not only because they're optical experiments, but because by comparing theory and experiment this way, you really understand what's going on in a problem that is sort of obscure, right? Why do we have resistivities above the Mott-Joffe-Regel limit? Okay, so now let's move to 4F electrons. And that was a little bit more understood when dynamical mean field theory came to the fore. In the sense that we understand the high temperature limit. At high temperature limit, we have some atomic electrons, which are the F electrons, and then we have a bunch of SPD electrons that don't see them, they just scatter of them. And then at low temperatures, we have some very, very heavy quasi-particles that emerge. So how does that happen? How do we cross over between them? That we really didn't know. And there are materials that do that. And again, I'll just show some work, but again, there's work by a whole community in it, which again help to establish the credibility of dynamical mean field theory through the same mechanism, the handshake. There was the cerium-115, which is like the Drosophila of the heavy fermions, the simplest material which has that. and has very, very strange optical conductivity with multiple peaks. And again, when one does calculations at high temperatures and low temperatures, one finds what one expected. At high temperatures, one has SPD electrons, and they just scatter off the Fs. At very low temperatures, we form hybridized bands, which are very heavy. But the nice thing is that we could actually relate the real material calculation to the peaks that you see in the optics, because there were two hybridization gaps. We were able to relate the structure to the different sites that there are in the system. And then that was a perfect handshake with experiment, all the way from low temperatures to high temperatures. So that sort of helped establish some trust between experimentalists and theorists, which is a small group of theories, those DMFT practitioners, which enabled great progress in a field which is actually very hard. And finally, let me show work by Ji-Hoon Shim and Jim Allen and Jonathan Dellinger, in which they really map in these 115s how the Fermi surface changes from a very large Fermi, the very small Fermi surface to a large Fermi surface, how KF goes shifting. And this is theory, and this is sort of the experiments we show the shift, and the comparison is quite good. And there's something interesting, and it's a message for this community, that both electronic structure and the MFT community, which is worth listening to, because until now, I mean, most practitioners in this field either treat the F electron as in the core and do a DFT calculation, or they treat the F electron in the band and they do a DFT calculation. And lo and behold, one of these two methods gives you a reasonable Fermi surface. What this group shows is that this is not quite the case for these heavy fermions. And in fact, contrary to what the community believe, neither one of these two paradigms are good, and you really need to do a full LDA plus DMFT calculation to get something which is close to experiment. Of course, it's not perfect. None of these things are perfect. There's a lot of room for improvement, but there's a lot of richness in this evolution from high temperatures to low temperatures.
Gabi,
okay.
I'll give you the 30 minutes bell.
Okay, 30 minutes. So I was going to mention the Hun's metal story, but maybe since Antoine discussed a little bit ruthenates, which is a beautiful example of Hun's metals, I will just say a couple words about this. And this is sort of the iron pnictides. And at the beginning, when people discovered that, they look quite strange. Some people would say, well, these materials are strongly correlated. Other people would say they're itinerant magnets. They all share these layers, but they have very different low temperature phase diagrams, completely different than the cuprates. All cuprates have the same phase diagram. All these pnictides and chalcogenides don't. Some don't have magnetism, some do, some different types of magnetism. So, and there are, again, lots of DMFT works on this. And the secret of this, and I want to stress one thing about electronic structure methods and having DMFT at your disposal, is that once you get a handshake with the experiment, like these groups do, one can vary parameters. And in these materials, the things are not sensitive to you, they're sensitive to the Hund's coupling. And that leads to very interesting physics that you can see in many features. This is the histogram. You just look locally what the electron is doing as a function of time, which atomic state you're occupying, and then you see that it's a metal. States with 4 electrons, 5 electrons, 6 electrons, 8 electrons, they're all equally possible. This is from a paper of Christian Howley. But inside each configuration, there's a preferred one, and that's that peak, and it's the highest spin. The charge and the orbitals are itinerant, very close to LDA, but the neutron scattering is very localized, and this is comparison of theory with experiment. So this is sort of, again, how we think about materials in DMFT. We start with atomic degrees of freedom at very high energies, and then we sort of go to lower energies. And as we go to lower energies in the Hund's metal, what we encounter is first the charge and the orbitals delocalize at this scale, but the spins remained localized until at very low temperatures, we reach a scale where the spins now get quenched, and then we have Landau quasiparticles. But of course, the story is a little bit more complicated than that. Sometimes the Landau quasiparticles become magnetic or superconducting, like in strontium ruthenium 04. Sometimes something appears at higher temperatures. Sometimes there's an orbital selective mode transition. And of course, these are words, but this goes with very nice mathematics, which is the solution of the Anderson impurity model through numerical renormalization group. And here I have to acknowledge the important work that was done in this area by the group in Munich in developing this. And this is a cartoon of the Hund's metal, which is a strange state of matter, where between these two scales, you have an orbital singlet, but you have maximal spin. Okay, so I will say only one more thing, which has to do with orbital differentiation, because again, this is sort of extremely important, and because it has to do with Hund's metals. The idea that all the iron pnictides are part of a same happy family was really a big leap of faith, because at that time people did not agree with that. DMFT done in this way reveal that there is a deep commonality with materials which have completely different phase diagrams. And that's the concept of the Hund's metal, that's the concept of Hundsness. And as we vary through the families, the orders at low temperature vary. Near the telluride end, there is what's called orbital differentiation. You can see that there is a band here that goes away at high temperatures, but there's something in common. The thing which is in common is that in all these systems, the local moment is the same. And of course, this has been seen experimentally in detail. So that's sort of the story with orbital differentiation. And then basically, I think is my time to conclude. I just want to say maybe one thing, since there was a question about phonons from the audience, and I mentioned sort of total energies and functionals. Maybe I will get to a slide which has the something about actinides. But as I said, it's not important that I cover that. I was just sort of going to say that in principle, there is an arena where DMFT has been very useful, which is the physics of F-electron systems. And it was useful because following Johansen, who was the first one to look at this problem, band theory, DFT doesn't work. For example, people did phonons for plutonium using DFT, and all the phonon branches were imaginary. So the system was completely unstable, even though this is the most stable phase of plutonium. And well, it was one of the triumphs of DMFT. And again, it was a blind leap of faith that the functional was used to compute phonons. Now people know how to do that much better. Here, we use Hubbard one type of approximations and an MTO basis set, but he made a prediction. And the prediction was not so bad. All the phonons were stable as they should have been and was observed experimentally. And again, it's this handshake with the experiment very early on that gave impetus to revealing the mysteries of a material. And then these histograms are a fantastic way of looking at this. If you do the histogram for a localized material like curium, you have only one valence. There's only one valence in a localized system, just like chemistry says. When you do DMFT, you have multiple valencies, and in fact, that's the secret behind the strange properties of PU, which is mixed valent. So now I will just go to my conclusion. I will not show you some photoemission or something about nuclear fuels, but I was going to say something about electron-phonon interactions, but I would like to say something maybe about future directions and more general perspective on the field. Of course, it's hard to make predictions. I mean, but it's clear to me that we need to, for the strongly correlated people, they want us to go to low temperatures because there's a lot of superconductors at low temperatures. And this field is very, very open for people with background of electronic structures. So that's something I really would like to work on and try to improve. And there's a whole community working on that, trying to reach lower temperatures, reach greater precision. And then we're going to say something about superconductivity in much more detail. I mentioned classes of materials. There are many more. Hunds, Mott, heavy fermion. There are a zillion classes out there, and understanding classes is very helpful. We want to get these complex phase diagrams. It's really important to take one more step and design something, because until we design something, people will not believe us. I mean, explaining experiments, predicting experiments is good, and DMFT has a good track of that. But I think that one should also say, okay, this is something new that has not been made in the lab. And DMFT is getting to the point that this program can be undertaken. And the other thing which is important is to try to be more controlled, and how basically, as we do things which are more detailed, the field now is much more technical. It's important to understand not only what's interesting to us, but also what's important to society. And I think the community working in weakly correlated materials has done a great job with structures like Psyche, which can talk about what's really needed to the material science community. We have not yet done that with correlated electron materials. I think this is something really important because there's a treasure of things to be discovered in the area of correlated materials. And sort of something in terms of how to get more precise. I mean, I like to think of a multidimensional space in the sense that electronic structure, real materials is much harder than models because there are many, many axes. We can think of starting with DFT, that's the Kohn-Sham-Green's function, and taking the heading axis of increasing order in perturbation theory. And we know this is not going to work for correlated materials because, as Antoine explained very beautifully, we need to sum things to infinite order. That's where DMFT works, and that's the locality of the DMFT axis, and we would do one side, two sides, four-side DMFT. So those are just two orthogonal axes. There are many more. There's the choices of how to embed, there's the number of K points, there's the basis set for the whole space. And in reality, we have materials and we have to explain what they do. And building on this is a great challenge. And that was sort of the motivation for this Fund DOE program at BNL. And with that, probably is a good place to say that more broadly, condensed matter is a very broad field. It has classical and quantum, model and first principles, universal phenomena, system-specific studies, first principle theory and phenomenology, multi-scale phenomena, the most fundamental intellectual challenges, and systems which sometimes lead to useful applications. These renormalization group equations for the Hund's metal are not different in principle from the renormalization group equations of quantum chromodynamics. I mean, in fact, they're richer than that. But the notion of the emergent phases in condensed matter physics out of strong correlations is really a unique field. But also we can do things which are applied. So this emergence and reductionism, the interplay between experimental information and development of abstract ideas, all that was illustrated very nicely by dynamic and meanfield theory, which provide a language with which we can actually talk to each other. And it's needed to have more synergistic developments of whole communities, new methodologies, new concepts. And I think that's sort of the story of the MFT. The development of these things simultaneously is the key to new understanding. And we need to have a more general dialogue. Where do we need more precision? What do we want to know? Where do we really need more qualitative understanding? This is, of course, important in all physics and all science, but I think it's particularly important in condensed matter physics because it's played a central role to face the challenges of society in the 20th century, and I'm sure it's key for solving the problems that we have in the 21st. And I think there's a treasure in correlated materials that we should exploit together. Thank you very much for your attention.
Thank you, Gabi, for the wonderful talk. Great pleasure. Let me again suggest for people to write their question in the question and answers, but maybe let me get started, and I'll go back to the phonons and the total energies because I'm very fond of those.
Yes.
And I guess you know, my prejudice was always that, of course, you know, you really need a spectrally resolved theory to get, you know, what is right and what is happening at the Fermi energy. But then the total energy is very much an integrated quantity. And a lot of boring electrons, if you want, take part in that. And so maybe it's not so important. Now, I guess you convinced me sort of in the case of plutonium that we have, you know, fluctuations between mixed valence states, and that truly affect the say total energy of the system. But maybe if we go back instead to the rutinates or some of the, say, d electron materials, you know, my sort of the question in the back of my mind is how much the dynamical correlation really affect total energies and derivatives compared to just, you know, a static limit where we have, let's say, a DFT plus U potential energy surface. What are your thoughts? What is your feeling?
Okay, that's really a very important question. And I would like to take a little bit of time to answer. I agree with you with the basic premises that for most things, we could do for the total energy something that is more primitive, that we don't need to solve the full many-body problem down to the lowest energy scales to get the phonon right. But at the same time, I feel that what precisely we do and how we do it, we need to have some intuition about the material that we're using. And that's where I would like to share my experience with one oxide, the barium bismuth oxide. Barium bismuth oxide is a high temperature superconductor. And my best friends, for example, Sergei Savrasov, was trying to convince me that this material is strongly correlated because he had done a DFT calculation and the TC that he had gotten is 1 Kelvin, where this material has 10 Kelvin or higher, even 30 Kelvin. It's a very important superconductor. And my colleague next door, Piers Coleman, was trying to convince me that this has some Kondo effect in the charge, and he had some theory that I really could not understand, but it was very elaborate with many parameters and very fancy concepts. But I looked at that problem first, and then I basically thought that in this problem, the most important correlations are essentially static correlations that needed to be treated with GW. And we sort of use GW and screened hybrid functionals to evaluate the electron phonon coupling. And we got a huge enhancement relative to DFT. And once we put that, everything fell into place. And we managed to get the correct TC, the correct electron phonon coupling, the correct structure. So this comes from high energy, but the GW is changing things at high energies relative to the DFT. But that's not the whole story. The optical conductivity of this material, and this is sort of experimental results, it's quite weird. It has a lot of incoherent spectral weight, etc. And it was also a challenge to describe. And here GW doesn't do a good job. What we need to do is we need to use the lambda that we derive from GW and treat the electron phonon coupling in DMFT. And now we can also explain that. And that's something that was done by Reza Nurafkan. So yes, I agree with you completely with your intuition. For the total energies, we really need to look at high energies, but sometimes, not always. Most often, DFT is great, but there are certain cases, and part of this Brookhaven initiative was to be able to do this type of system on the same footing as we do, say, plutonium, try to have something more uniform. What we would like to do is require less intuition into a problem and have a machinery that encompasses everything. And we're not there yet, but your intuition is correct. We have many separate examples to show that. And I should say that since we wrote that paper, the group of Steve Louie in Berkeley has built on that, has developed more sophisticated tools to evaluate the linear response with GW and confirmed basically all what we said about barium bismuth oxide. So this is a success story. And the way I sell that is I say, well, dynamical mean-field theory is very important, but it's not everything in life. And it should be viewed in a universe of electronic structure methods where we want to treat both static and dynamic correlations because both matter for different things in different ways. And so I don't know if I answered your question with this example.
Very much so. But also, I mean, this slide, prompt me the question that I wasn't sure I should be asking, but I think I could blame you in prompting this question because you say other high TC superconductors. I mean, here you are saying, correlation enhance, a mechanism that we understand, an electron phonon.
Yes.
What do you think about the other that these days includes also twisted bilayer? I know I wasn't going to ask, but I saw this.
No, I mean, again, I wear different hats because I like to do both sort of fancy theory, and I also like to do things which are down to earth when I can get funding for it. And I think that each system, I would like to dream that we got to these correlated materials to the same level that we have in DFT, that we can answer those questions because we studied so many density functionals and corrections around them, and the codes work so beautifully. So I don't know. I know that this mechanism that correlations and enhanced electron phonon coupling has been demonstrated in one case for one phonon in iron selenide, because my colleague Christian Howley made a prediction for iron selenide that there was a very specific phonon whose coupling to the electrons was very enhanced. And then through very interesting spectroscopic measurements, the group in Stanford verified this correlation enhanced electron phonon coupling. And their DMFT was essential because of the Hundness. But I also know hundreds and thousands of materials where DFT gives you really accurate values for the electron phonon coupling. So without having had the chance to work and play with the system, my honest answer is I don't know, and you shouldn't guess. These things require some computation, some play to get intuition into the system, and then I will be able to tell you something. So I really don't know for the bilayer graphene.
Okay.
Did I answer your question?
Yeah, well, I mean, in part, and the other part is probably a Nobel Prize in the waiting, but no, absolutely so. But it also sort of cues in to another question that maybe is more trivial, but we often have, let's say, an electronic structure audience here that is more DFT oriented. I think the intellectual picture is clear from today, but what about the numerical and computational picture? That is, how difficult it is to systematically expand the number of orbitals that you correlate, the number of sites, we have mentioned before a cluster, the MFT, or just, on a single site. What do you see this as, are real challenges that are more on the numerical computational side? Is just a matter of time?
Well, again, that's what I brought here. This is my view of the condensed matter field, and I think that there is an important area, which is the development of better algorithms. There's an important area which takes advantage of some new ideas. And for material science, the important question is, what do we really want to know? We don't have a hammer that can be used for everything, in the sense that DMFT right now doesn't scale as well as DFT ON implementations, okay? But we're working in the context of this project, and maybe I should have spoken about this, but in 40 minutes, I cannot convey a flavor of everything. I believe that there are some quantum embedding methods which actually bring a whole circle the history of dynamic mean field theory and infinite dimensions, etc., and strong correlations, because they bring together many things. They bring together variational wave functions like the Gatzwiller wave function, and one of the early successes of this was to evaluate Gatzwiller wave functions in large coordination. And then there are also some slave particle methods that are similar to the Gatzwiller approximation, and Ismail Shoraf-Beji has developed that more towards electronic structure. So there is that set of ideas that looked completely disjoint from dynamic mean field theory. But it turns out that now that we understand the field so much more, we can view those things as cheaper quantum embedding methods. And I think that those cheaper quantum embedding methods will be the path towards what you would like, being able to do many impurities and being as fast as LDA plus U, and get the total energies right and the structures right and control the method. So that's, I think, my bet on how, and that involves not just improving the algorithms, even though improving the algorithms is extremely important. It's not just improving the codes, but also thinking deeply about these embedding methods. And I have to say, the light that dynamic mean field theory has shed is enormous here, because I worked on these slave particle methods, Antoine has worked on the slave particle method, but we always thought of them at the time as sort of alternatives to quantum embedding methods. But now it's clear that it's a quantum embedding method, so that the concepts are also of value.
Yeah, no, I think I fully agree with you, so I'm very glad. Thank you. Let me take a question from the audience. Christopher Jacobs says, we have spoken about strong correlations, but then you have dynamical mean field theory. And so maybe, a good question just for a general audience is that, we tend to think at strong correlation as static. Do you have in your mind a good definition of what are dynamical correlation and what are strong correlations? And
Sure. I mean, I should have brought my slide. It's usually my first slide when I teach in a school. The definition of correlations is important, is somewhat arbitrary, because if you talk to a chemist, the chemist will tell you that correlations is how different is self-energy from Hartree-Fock.
Yeah.
Of course, for us condensed matter physicists, Hartree-Fock is terrible, and that's not a good definition of correlations. For us, I take as my definition of correlations, going back to my first slide. For me, my definition of correlations is I just take my material, I look at the self-energy, which is a well-defined concept, and I ask, how different is this self-energy from the Kohn-Sham potential from DFT. So I go here. So for me, I just take the real self-energy of the solid, either from experiment or from DMFT computations, and compare it with the static approximation, which is the Consham. If this difference is large, then I say the material is strongly correlated. If this difference is small, I say this material is weakly correlated, and immediately I know what to do. I will just evaluate this correction, and if need be, the next correction, and I'm done. So it's a working definition. Now, so that answers the question, what is strongly correlated and what is not strongly correlated? Now, the second part of the audience question is static versus dynamic. And for that, what we need to do is introduce the, like Antoine said, we need to introduce the and by the way, this is an energy dependent concept, because at very high frequencies, you always go to Hartree-Fock, but we don't care what's the energy at 10,000 electron volts. We work in the 1 electron volt region, so it's a low energy definition. So now, to decide what's static and what's dynamic, we need to look at the true self-energy of the solid and see if it's strongly K-dependent or it's strongly omega-dependent. If it's strongly omega-dependent, we need to do the MFT. If it's strongly K-dependent, we need to do GW. And I show examples with the barium bismuth oxide. I realized immediately that I had to do GW because the oxygen positions were completely wrong in the FT. And I realized that that was very important. So, and I knew quasi-particle GW would fix that. I also can tell, I didn't have time to tell you this element and the story about nuclear fuels, but for actinides, the dynamic part of the self-energy is everything.
Yeah.
And there's no need to do GW. I mean, the quality of the GW in actinides is comparable, sometimes worse, to the quality of the FT.
Yeah.
But when you do the MFT, you get the physics right. Instead of predicting a 5-Bohr magneton that is not seen experimentally, you predict a non-magnetic state. GW gives you 5-Bohr magneton.
Okay. No,
so I think I explained static, dynamic, local, and non-local correlations.
Yeah.
And it's a definition, but it's a good definition, because a good definition is something that it's clear, but also tells you what to do.
No, thanks. A point taken. I think, Gabi, with this, probably just to keep everything to a reasonable time, maybe we conclude the talk side. So thanks again. It was really a great pleasure. To be honest, I would stay hours discussing. And
me too. And we should find some venue to do that.
I'll ask that in person. And one of the sort of characteristic things of this second Marvel Classic is that we also sort of end up with half an hour fireside conversation, because I think it's very nice to have a chance to explore a little bit more the broader sense of what is the scientific endeavor, and get to know maybe also some personality side of things and so on. So thanks, Antoine, also to come back. And again, we have the question and answers open, so everyone in the audience is very welcome to chip in. But maybe again I'll start. I was looking at your 1992 paper, and I'm afraid to say that the World Wide Web didn't exist. That sort of started coming out in 1993. We had emails, but not the World Wide Web. So I think, I just would like to do a little bit of a time machine and ask you, how this all started for you. How, did you get to know each other? How did you get to work together? And somehow, I mean, you both mentioned, Antoine was coming maybe more from the statistical physics side of things. You mentioned spin glasses also. So, how did it start, basically? Who
wants to start?
Antoine, you start.
Okay. Well, yes. I think it's, from the intellectual point of view, there is an obvious a commonality in our scientific background. So I have a background originally from my PhD years, which is more into the statistical mechanics of disordered system and field theory and things like that, spin glasses, anomalous diffusion in disordered media. And Gabi will say for himself, but I think he also has that training from especially his day in Israel. So that definitely was a common background, but the way we came into that was different. I mean, as far as I'm concerned, probably also for Gabi, the high-TC discovery in 1986, although of course the field of correlated electrons has a much longer history going back to the end of the 30s, but the discovery of high-TC was really a trigger. I was not done with my PhD at the time, but it implanted in my brain that really after my PhD, I wanted to go back to actually go to quantum many-body theory and strongly correlated electrons. And this is what I decided to do when going to the US. Of course, Gabi had a lot more experience than me in that field. He had already done auxiliary particle methods, predicted D-wave, done the famous Kotler-Rockenstein bosons. And I think this was a little bit of the end of a cycle where new methods were needed. And it happened that Gabi was a professor at Rutgers and I was a postdoc at Princeton. And I think we had a phone call in the fall of 1990 that I remember very vividly, where we knew each other, but we seriously touched base and connected at that time and decided to go for trying to address correlated electrons in this limit of large dimensions that Metzner and Volhard had pointed out, and try to solve the problem. Right, Gabi? This is also your recollection.
That's completely right. Yeah, and I should say, I mean, I did a lot of StatMech in the early days. I mean, my advisor, wrote a master thesis with Daniel Amit, and that sort of was field theory in StatMech. And then when I went to Princeton, my advisor, Phil Anderson, put me to work on spin glasses for all things, and I interacted a lot with Chaim Sompolinsky at Bell Labs, which had done at that time the dynamic mean-field theory of spin glasses in classical setting. So, I mean, I was very fond of those ideas all my life. And yes, and with Antoine, we had a common language and a common interest. I had essentially arrived to Rutgers, and I knew that I wanted to basically look at the strong correlation problem from this perspective, this StatMech perspective, because I felt that, yes, we have been able to do some things with auxiliary particle methods, but there was a need for a control limit because the community would not buy the results that came from control methods, for non-control methods. There's a problem when it's hard to decide what's correct and what's not correct. This handshake with the experiment, this dialogue with the experiment that dynamic mean-field theory has established was not available at the time. So everything was very qualitative. And I thought, okay, I mean, just to give you just an example, I mean, with a student at MIT, we basically developed what now Phil says was the correct theory of high TC with the D-wave superconductor, the pseudo gap, but nobody believed it. Even Phil didn't believe it at the time. So when now one does something with dynamic mean-field theory, people now take it a bit more seriously, because there's the control method, there's the possibility of checking that the calculation is right by improving things. There's this close handshake with the experiment. So that's what we were striving at. That standard in statistical mechanics, it was not standard in the theory of correlated electrons. I mean, in StatMech, we know we first do mean field, and then we do a renormalization group, and then the RG tells you when the mean field theory fails, and that's it. I mean, we can do clusters to improve the short distance. There is an established path. At that time, in correlated electron materials, there was no such a path, and it was clear that StatMech would provide that path. What was not clear, and that's the work that we did with Antoine, was how to do it. But the direction was clear to me.
But in this, was there a eureka moment? That is, was there a moment where you say we have a sort of broken some intellectual ground, or it was indeed a path?
Yeah, no, I think there was. I think what Gabi said is very much to the point. Looking at the strong correlation activity at the time with this culture of trying to find a control path through the theory, there was an obvious thing to be done, that to come up with something that can be grounded and controlled in some limit and then systematically improved. We were inspired by the large D paper of Metzner and Volhard, and also I have to say, I want to quote these names because they are important, by the papers on Fermi liquid theory in that limit from Müller-Hartmann, and the papers on the Falikoff-Kimball model by Brandt and Milch. So we had the intuition there was something there, but that the problem was not solved. And we struggled for a few months, right? I mean, we were hiding in my office in Princeton. Sometimes I was going to Rutgers, and we were frantically trying to derive these equations. And honestly, I mean, I don't think this is reconstruction, from of the past. Frankly, when we actually got this thing consistent, and we had these DMFT equations, I think we knew we were onto something. There was a bit of an epiphany moment where we knew we had gotten something relevant. And in fact, very early on, we also thought this was going to be relevant for materials. When our first, the 1992 paper, which is really a 1991 paper, by the way, but when this paper was sent to PRL and rejected, we thought, okay, maybe we should rewrite this paper and write it as a theory for the satellite excitation of nickel, because, and we didn't do that, but there was another important moment which came a year later when I was back in France, and Gabi with Marcelo Rosenberg and me with Werner Kraut embarked into actually solving these equations, because our first paper didn't really solve them except in some approximate method. So when we went to actually solving these equations, we realized that these equations had the mode transition, which was not in our first paper. And these are two independent papers that we published the year after, still 1992. But, and that was another moment in which we knew that there was something there.
Yeah, no, fascinating. I hope you still have the referee reports from the PRL, but I think it's also a good encouraging message for all the students. That is, if you get your papers rejected, I think there is hope, and actually, the more out of the, say, mainstream they go, the easier it might be that they get rejected. But it's not a reason to.
Very true.
Yeah. But now, sort of just staying at that time, I never made the connection, but, both the PhD advisor of Gabi was a Nobel Prize. I don't know if Dejean was either your PhD advisor or sort of involved, but so you guys grew up in an environment where they were all sort of, Nobel Prizes or close. Did it play an influence? Did it sort of push you to be ambitious, but in different directions? Was it irrelevant? You learn what one should do, what one shouldn't do, or, how was it?
Well, for me, I mean, being able to witness and interact with Phil Anderson was a complete education. I mean, just being exposed as a student to so many aspects of condensed matter physics was a real eye opener. I mean, the love for the field, how broad things were. I mean, how broad the scope of that was really incredible. I mean, I think that yes, I mean, I think education is everything, and I think more generally, because Princeton or École Normale are elite institutions now, I think our challenge, we live in a different world, and the problems for society are bigger. We need to think more about how to make all these things more public. And I like this series because it gives a massive opportunity to people to talk with cutting edge researchers. So yes, it was extremely important for me. My advisor, I wrote only one paper with him on spin glasses, but just being able to talk to him every now and then and see what was going on around me, the environment, the scientific environment, I think is essential. And I think our challenge now is how to make that go from elite universities to everywhere in the world. And that's why your series, I think it's a good idea.
Thank you, Gabi.
So on that point, I think my experience is somewhat different from that of Gabi. I had a very, very unusual experience as a graduate student. Really, you know, I only had a formal thesis advisor. My thesis advisor was a high energy theorist, and I'm guilty of a few initial papers in supersymmetry and supergravity, actually. But I was basically left on my own to a large extent when I was at École Normale. And I was left on my own basically to find and define my own research problems, which was both very, very scary and an incredible opportunity. And what happened is that I teamed up with two fellow graduate students at the time who were incredibly bright and who really shaped a lot of my first steps in science. And these are Jean-Philippe Bouchot and Pierre Ledoussat, who both did you know, fantastic careers in physics and in other things as well. And we really grinded our teeth on a whole set of questions that we defined for ourselves. You mentioned Dejean, but Dejean was a very influential figure for us. So was Edouard Brezin, for example. But Dejean was the president of my PhD committee. He was not my PhD advisor. So we really worked on our own, and we had a few mentors who helped us along, people like Claude Bouchiard, Alain Comté, already mentioned Edouard. But we really I really had this incredible experience of as a PhD student trying to find my own research problem with a couple of really good friends and fellows of my same generation. Then for me, the move to the US as a postdoc, my postdoc supervisor was also Phil Anderson, so that's something we share with Gabi and also Daniel Fisher. Actually, I was shared between the two. But moving to the US was a transformative experience because, you know, as a French student, I learned to answer the question, you know, how am I going to solve that problem? So the how was everything. But in the US, and especially being exposed to you know, almost every day's discussion after a while with Gabi, I realized that you have to ask, why would you want to solve this problem? Not only how would you like to solve this problem, but how and why? Why should you do this? You know, and this is the how and the why that combined together, I think, made me a more mature scientist. So I could combine these two cultures into something that I enjoy.
I completely agree. It's actually the advice I give to all my PhD students to indeed, you know, experience also the you know, very lively US.
And then, you know, something else I want to say is that you're also influenced by people who are younger than you. And I was very fortunate to have some incredibly talented graduate students later in my career, like Olivier Parcollet or Serge Florence, also fantastic postdocs like Jan Emovir, Corinna Collins, Ilka Bierman, Leonid Borowski. I mean, all these people really fed me with a lot of ideas and ways of seeing science. Gabi and I exchanged students and postdocs for several years, you know, people like Marcello Rosenberg, with whom Gabi had done the mob transition, and Olivier Parcollet, Giulio Biroli, you know, Marcello Civelli, Luca De Medici, Camille Aron, Fabian Kugel, many people who went back and forth between our two environments, and that also shaped our way of doing science, right, Gabi?
Yes, and I would like to add one more thing that in common with Antoine. I mean, in my PhD, I praise Phil for the diversity of interest and all that. But in my PhD, in terms of working, I was entirely on my own. So in terms of how to solve a problem, that's Phil's attitude. I mean, the student
that's something we share. That's you and I share
by himself, and that's invaluable. And I think that once you do that, I mean, I always say that when the postdoc was trivial in comparison with the PhD, because it's extremely hard for a beginning person to try to have to do everything on his own. But I still, and of course, as an advisor, as a PhD advisor, I'm not like that. I really try to define well-posed problems for students because because I think in some sense it is a duty. But if there are people who are able to do things entirely on their own, that's the best experience, and I encourage those. So depending on the type of student we have to basically live on their own or guide. And I think that this mode has to be adapted to the student. Phil would not do that. I mean, with Phil, at least all my classmates were entirely on their own, and that was always the subject of complaints and conversation. But it shapes you, and I share that with Antoine, and it helps working in science a lot afterwards.
Yeah, I think if you exactly survive the experience, you then have the energy and the drive. But it's never clear if it's the best sort of solution to throw.
Well, I mean, this could have been this could have been a deadly experience, but if you survive that, this is actually very strong. But by the way, I mean, since Gabi mentioned Phil so much, I mean, it's very interesting to see that once we wrote our first preprint, Phil got very excited and about this DMFT idea, and he made all sorts of comments and very early on, like, a month after our preprint was written, we were engaged into discussions about that. And yeah.
But then let me send you back to sort of, being again a PhD student without a project and without a field. So you are now, 20 something, and you have to figure out what to do. You mentioned before ITC somehow was really stimulating.
Well, that was before, I mean, my early steps in as a graduate student was 1983, 84. So it was before ITC. Yeah.
But so what would you do nowadays if you were, to start from scratch? You are a sort of, you have a broad education in physics, not necessarily condensed matter. And what do you think you yourself would launch you? I mean, especially if I would forbid you to work with correlated electrons, because let's say the problem has been solved.
Well, I don't think the problem has been fully solved. I think there are some very promising parts, and it's a very rich field. So, there's lots to do there. I don't know. What would you say, Gabi?
Well, I mean, I would convince students to work in strongly correlated electrons. I mean, I would convince students that that it's like a rich field. There's a lot to be discovered. Just like I give 3 examples: heavy fermions, Mott systems, Hund metals. Hund metals, it's fairly new. I mean, in some sense, our field, you ask me, when did you know that you're doing something important? All the time, because it keeps giving you new discoveries. And it's not just that we turn the crank and we explain an experiment. Some new concepts pop up. That's how science in this field makes progress. We look a little bit of nature, we do a little bit of calculations, we confront, we play, we think, and then some higher level concept emerges. And this can be done again and again in this rich field of correlated electromaterials. Like Antoine explained, we understand two limits. In high energies, yes, everything is done, is atomic physics. At low energies, most of the time, you have some order state, or you have a Fermi liquid state. Sometimes you can have a spin liquid state, but it's very, very, very rare. But in between, there's still a lot of land to be explored. So I would, right now, I mean, I would recommend the student to do that. Plus, it has the bonus of what I was trying to stress in my talk about condensed matter theory, that we can also do useful stuff. I mean, we might be able to, if you look at the number of Nobel Prizes in condensed matter physics, it's about half. I had to give, now I'm doing a law administration against my will, and I had to give a talk to the administrator. So I looked in the last 30 years, there's a blog by Mackenzie that describes how many Nobel Prizes were given, nearly half. And it's in applied and basic, broad condensed matter physics conceived. So I think that's the field. I think condensed matter is the field. I also consider at some point to do high energy physics. I was very lucky that I didn't pick that field. When I went to Princeton, my original intention when I applied as a student was to actually well, I was trained as a field theorist, so I could do either one, but I was going to do particle physics. But then after a little bit of time, I decided that that's really not the way to go. So I would advise the students to do CMT, condensed matter physics, and I would ask to actually focus on correlated electromaterials, but at the same time do electronic structure so that they can also connect with reality and maybe be in this 50% of the Nobel Prizes for useful stuff, where the concept was known, but you know, I mean, LEDs, solar cells, all sorts of stuff is useful.
So Nicola, you know, I'm not going to answer, I agree with what Gabi said, but I'm not going to answer your question exactly in the same way by pointing at a field. I think doing correlated electron theory and more broadly speaking, condensed matter physics is absolutely great. There are fascinating things ahead. But, you know, if you take a somewhat broader perspective, what I would say is that it's really important to work in a field which is connected to nature, reality, and experiments. That's really, really important. And somehow I made a decision about two years into my PhD not to continue in high energy theory. Not because I thought the conceptual edifice was not attractive, it was very attractive, but because I could foresee, or I was afraid of having a long, even though I was a theorist, of witnessing a long desert of absence of really new experimental discoveries. You know, there's been fantastic things confirming the standard model, but new things that nature tells us that we didn't know before. And I couldn't stand that. I thought we absolutely I absolutely want to be in touch with new things that nature is going to bring. And I agree with Gabi, this is, you know, the field of materials in general, correlated or not, is constantly full of surprises, which keep me alive and in awe of as the diversity of nature. But you can find this stimulation in other fields, in many other fields. I think chemistry, for example, is absolutely amazing. Just to name one thing, or ecosystems, you know. But you have to keep this connection that these are natural sciences.
I cannot hear you.
We can't hear you anymore.
Oh, I just muted myself.
Yes.
I was saying, the questions are going to get more and more difficult at a certain point.
Aha, interesting.
But, you are both extremely happy and enthusiastic, and it's, in some ways extremely refreshing seeing all this. But do you have scientific regrets? Do you have a sort of, thoughts about saying, I should have done things differently, or I shouldn't have done this? And if you have, I see Antoine nodding. What can you share those?
Well, actually, at some point, I promised one of my colleagues in France to prepare a seminar for second-year master students about listing all the things I consider I missed in my, I could have done in my scientific life and actually missed. I think this is an extremely humbling exercise, but also, in a sense, a very stimulating one. So let me quote one example. I mean, if we just talk about things that I wish I had done but didn't do, just from a purely scientific point of view, let me just quote one, okay? Because I think it's a very instructive example. So in the early 90s, after I was back from my postdoc and desperately trying to solve the DMFT equations and talking to Gabi, I guess over the phone, we didn't have Zoom at the time. I was in a context where my colleagues, one floor below, were actually cooling down atoms, right? I mean,
yeah.
The Nobel Prize of Koen-Tanuji, ultra-cold atoms, and so on. And I was exposed to all these colloquia where, well, the idea was to reach the Bose-Einstein condensate and go to the most perfect gas you could to reach the Bose-Einstein condensate. And I thought, well, it's very interesting, but this is not for me. I'm interested in strong interactions. Exactly in the same place, in the same lab, on the same floor, there were pioneers of optical lattices. The first block oscillations were, for example, with at the time thermal atoms were demonstrated in that lab. So here was this guy solving the Hubbard model on the second floor, and these other people cooling down atoms and having developed optical lattices on the first floor. And it was so easy, retrospectively, to put these things together and say, okay, let's actually make these atoms strongly interacting by confining an optical lattice, and we're going to do strong correlation physics with cold atoms in optical lattices. Well, we didn't write these papers, right? This paper. The Action Zoller did, and others. Why didn't I write this paper? Well, on top of that, I was collaborating with Werner Kaut, who had worked on the Bose-Hubbard model. So all the elements were there. Why didn't I write this paper? Well, because I was, in my cage of, I was exposed to many things and I learned on many things, but I didn't make the connections. And you have to keep a very open mind. When you listen to a talk, and this is probably the useful part of that speech, when you listen to a talk, you can be very conservative and say, okay, this is not for me. I need to go back to my office and solve my problem. But maybe not. Maybe this is a problem for you.
Yeah, no, very, very, very good point. I'll start to think at my own regrets.
I have a list like that, but I don't want to go through the whole list of my failures. But we can discuss this over a coffee. I have a list.
With pleasure. Gabi, what about you? Your biggest?
Well, I mean, when I think a little bit about my life, what I see, I mean, if I want to mention one regret, is that I was not more involved with the community. I was always a little bit of a loner, in the sense that, okay, I have my collaborators, I have the people I like to talk to, and I don't really care what people think of what I'm doing. And now that I'm much older, I'm beginning to recognize that we're part of the community, and that's not really enough. It's important that not to be aggressive, but to at least voice what we think about a problem. Because if everybody stays quiet, then we're missing a great opportunity. And it's from my personality. I'm sort of a little bit shy. So I always had good problems to work on, and I was always happy with my science. But I never had really the courage to say, well, that's not enough. I mean, we should interact more with people. We should say what we think, and we should try to contrast different points of view. And now I'm doing it a little bit more. And finally, I'm willing to take some jobs which have some responsibility. But for many, many years, I guess I didn't do that. And I think that now that probably was a mistake, because I would have been more exposed to more things, and probably I would have been more effective as a scientist.
Yeah, no.
I would like to say a few more things, Nicola, about this notion of community, because I think this is very, very important. So let me say a couple of things about that. You know, the community of correlated electrons in the early 90s, which is when I entered, it was not particularly congenial. I think it was very intimidating for a young person like me coming from a different field, very intimidating. And I think retrospectively, we could have stood up a little bit earlier and say, okay, we need to create a different atmosphere in this community. I'm actually very, very happy that this has been happening for the last 10 or 15 years. I think the community is behaving and functioning in a much, much better way. The internal discussions within the community are way more congenial. And I'm very grateful to the new generation of people to have made this possible. I'm also very excited and grateful for the fact that I think in the field of computational condensed matter physics and many-body theory, we are witnessing a very, very interesting and exciting time. This is why for young people, it's also a good time to enter, which is that the different methods that have been developed are now able to work together and converge in some region of parameter space and some observables that both types of methods can calculate, so as to actually establish certain things about, say, correlated electron models without the shadow of a doubt. And this is a big transformative thing in the field. That's what I call the handshake between the different methods. And you know, this has been made possible because the methods have evolved. For example, wave function-based methods are now able to go to finite temperature and make their way up in energy. DMFT, embedding cluster DMFT methods have been able to go down in energy. So there is a common territory where to talk to one another. Monte Carlo methods address this problem in different ways. And it's been also promoted by institutions. You know, I think, for example, the Simons many electron collaboration that Andy Millis created played a very big role in this. And we try to maintain and expand this philosophy within CCQ. And I think this is very important for the community. So we live in a time where things are very exciting because there is this handshake between different point of views. And we realized that actually it's like a landscape, you know, which was very foggy and you saw only little pieces. But with this handshake, now the fog is going away and you see that there is a coherent landscape, that the different methods used to see different parts of the landscape.
No, I absolutely love this statement about the community and also the excitement. I share all this excitement, and maybe I should even mention, since it's a second Marvel Classic, how much these transversal efforts like SECAM or Psyche have actually played and play a very important role in getting people to work together, exposing people to...
Or open source code. I think, for example, effort that we both described in our talks, and which is all over the world in many fields, of putting in the open the codes and algorithm is very important. So Gabi mentioned the ComSuite effort at Brookhaven. I would like to mention the TRICS effort at CCQ. We're going to have a TRICS school this summer. And you know, this is very, very important also to create this atmosphere in the community of exchanging not only ideas and concepts, but also concrete tools to do this computation.
Actually, that is incredibly dear to me because, you know, I see codes like you do, you know, really the scientific infrastructure of our research, exactly as, you know, people need to build, you know, square kilometer arrays and synchrotrons. I mean, you need to build this scientific software infrastructure that at the end.
Absolutely true.
That's what we do.
Yeah, I think there's a huge room to convince society that science can do a lot for society, but science needs a lot more support.
And it's a collective enterprise. That's also very important to emphasize.
But it's a collective enterprise, but where individuals can do their own thing and create their own things. That's why I always go to the diversity of the condensed matter community, that you can have algorithms, you can have concepts, you can have ideas, you can have ab initio, you can have phenomenology, you can have experiment, everything interacts. And there also has to be some awareness of societal needs. And I think that this will require a lot of dialogue, but it's a very, very important concept to get across. And the fact, I mean, I work on correlated electrons because that's what interests me. But I feel that the field is, of course, a lot much bigger than what we've done. Many people have contributed there. I want to express my thanks to all my students, all my postdocs who have done things really amazing. And I would like basically to make sure that there is a home for research efforts like that all over the world, and that they're better coordinated and they're recognized by society, while at the same time we recognize the societal needs. And for that, we need to speak as a community. So this is, you asked me about my regrets. My regrets is it took me 65 years to really understand that, but I think this is a very important thing.
Thanks. I think, yeah, this is a beautiful note. I think we are almost coming to a close, but I really like this message. And, you know, if I could even reiterate, I mean, I always say it's a very, you know, democratic field, because indeed the scientific software can be shared worldwide. Intelligence and knowledge can be shared worldwide. And so it's something I think we are all very proud.
And I think there is a sort of magic triangle, you know, between theory, concepts, computations and algorithms, and experiments. And having this magic triangle function together, and I would add, you know, material discovery, obviously, and chemistry. I mean, all these things working together makes for a fantastically stimulating intellectual environment.
Yeah. Yeah, and that reminds me, if I would tell a student what to do, I think material design is, and I would quote Feynman, who left on his blackboard that in order to understand something, he has to construct it, he has to design it. That was sort of his famous last words on his blackboard, where he left the problems that he had already understood, the Kondo problem, superconductivity, this and that, and the problems he had not solved. And I think that will be really the proof of the pudding. It's a very hard challenge, but that's what we need to do. And yeah. I think that once we do that, society will be nice to us as well, and then everything will work out.
Thanks, Gabi. Listen, before closing, you know, there is an almost personal, but it's an easy question that I borrow from, you know, the Desert Island BBC show. And that is really, you know, to give a glimpse of your own cultural taste. And so I always ask, you know, if there is a book, there is I used to ask a CD, probably now I need to say a playlist, but if there are these two things that you would take on a desert island with you, what would you take?
Are we allowed for more than one answer?
Sure. This is go ahead.
Well, on the music side, I would definitely take the cello suites of Bach. These are among the only piece of music that when I listen to them, I can do science at the same time, and my science gets better, actually.
Do you have a favorite one?
The number 4.
Okay, and played by?
Ah, that's a more complicated issue. I could say Casals, maybe.
Okay. And what about a book?
Oh.
Books, there are many. When I was younger, I used to absolutely love Stendhal because it satisfied my young person
Dramatic.
energy and drama. But I don't know. I'm into more quiet things these days.
What about you, Gabi? I saw you thinking in the back.
I was thinking because I never asked myself that question, but if I had to take a book, or a couple of books, my favorite writer, and Antoine may like this, is a French writer, Albert Camus, and I would take L'Étranger or La Peste or both, especially after the COVID pandemic. It sort of reflects a little bit who I am and my view of the world. In terms of music, I really don't know. I mean, I would take all my playlists. I mean, right now, I don't see any reason why I should be limited. I can store as much as I want. I would even maybe get a subscription to Spotify.
Okay.
So I don't know. I mean, I don't think I would have a one.
But Nicola, rather than a desert island, which is not necessarily the place where you do most creative things, I would rather pick a little cafe that Gabi knows very well on Place de la Contrescarpe in Paris, where we spent wonderful hours, Gabi and I, working on various physics problems. I would rather spend my time there.
Okay.
Yeah, and in
Or
fact,
in the beauty of nature, in the mountains.
Agreed.
Point taken. Listen, thanks a billion. This was incredibly enjoyable. Thanks for your time in putting together also these talks. They are recorded for good, so they are meant also to be a resource for young students that they want to know both the science, taste in music and books, and hope to see you soon in person. Thanks again.
Thank you very much. I think this is a wonderful series. Thank you very much for including us.
Bye-bye. A pleasure as always, Nicola. Bye-bye.
Bye. Great pleasure for me. Ciao.
Ciao.